The foundation of our specialty is, of course, our disease model, a model we feel has been verified repeatedly over and over again by very careful clinicians and researchers for over 60 years. Now, much of this research is the result of incredible commitment by researchers, and I don't want to disparage it in any way. It's the conclusions from the research and the inferences we draw from this work that is where the problem is. In the language of logical inference, the proper way to frame this is microorganisms are necessary to be present for the development of apical periodontitis, but it does not follow that microorganisms are the necessary and sufficient factor in apical periodontitis, because many cases have large numbers of microorganisms present, yet show evidence suggestive of healing or at least surviving long term. So our model needs to account for these cases. It needs to give a biologically plausible explanation for how cases like this can actually be successful. If you don't know what is both necessary and sufficient for a disease to occur, then you can't even begin to claim that you know what the cause of the disease is. So, in my view, we don't actually know what causes apical periodontitis. We only know that microorganisms appear to be necessary for the development of the disease, but we don't know what is necessary and sufficient for the disease. We have very little knowledge of the confounders of this disease. Our model is based solely on idealized counterfactual experiments that fail to consider the complexity of the disease we treat. The only real test of a model is, can it explain what we observe? It would also be advantageous to have the model have some biologic plausibility in its mechanism. The model must give an account for how cases such as this can be successful. To claim that such cases are successful because we have reduced the bioburden or starved the bacteria to death, or reduce the substrate below a certain significant level, or my favorite, sealed the canal so bacteria can't get out, these explanations strain credulity and simply aren't plausible given what we know about our ability to address the anatomy. Our model has to explain the success on cases like this of John's, where clearly all substrate has not been removed, where the irrigants can't possibly have had much effect at the terminus, and where at most you have a single cone obturation. Yet these can be very, very successful cases. So hopefully we have some agreement that our model does not explain fully what we all observe. In other words, there's a bypass. And I think we should recognize that we come to our task with significant bias from our training, and that bias may trick us into thinking we know something when we really don't. So why can't our model explain these things? Well, the planktonic disease model, the Cauchian model, is essentially different from the biofilm microbial disease model. One is continually supplying organisms to the host. The other, only in its dispersal phase, is it shedding organisms. And planktonic disease is monospecies and monoclonal. Biofilm disease is polymicrobial and polyclonal. In planktonic disease, one microorganism. In biofilm disease, there are many species and a very wide distribution of disease states. And as Garth Ehrlich has taught us, biofilms are phenotypically and genotypically totally different from planktonic organisms. The take-home message is this: Koch's postulates really can't be fulfilled because it's impossible to duplicate all the variables that are involved in disease expression. Additionally, Koch's postulates do not allow us to readily address naturally occurring environmental, genetic, and other relevant factors that influence disease causation. And they don't allow us to consider the pathogenic complexities induced by sequential or simultaneous infection with polyclonal and polymicrobial biofilm subtypes that we know characterize such infections. I think it has been shown beyond reasonable doubt that endodontic infections are biofilm infections. There are cases where planktonic organisms are growing freely and may mimic Cauchian epidemic diseases, but certainly in retreatment cases, we are dealing almost exclusively with biofilm disease. You'll notice in our experiment, even the area that is not stained with the EUB probe, that's the area of the canal that has been covered up with sealer that stuck to the canal and wasn't removed. Underneath that sealer, one would expect to find the remaining biofilm. I think that David and my disagreement really revolves around the status of that biofilm. He might characterize it as dead or the canal as bacteria-free. I would characterize the biofilm as resting, dormant, or in a VBNC condition, viable but not culturable. Proving one or the other is going to be a very difficult scientific problem that is going to take some committed research. The bacterial biofilm life cycles, there's various phases to this, and the key to understanding biofilm disease, in my opinion, is that the resting phase is really one that is very poorly understood. The major key to understanding this is that the biofilm mode of existence has phases, and that in environments that are hostile, the dominant phase is the resting phase. One might characterize a treated tooth, even a poorly treated tooth, as a hostile environment from a biofilm's perspective, especially given the environment that caused the biofilm to come about in the first place. This resting phase is not like the stationary phase known to microbiologists, as we will endeavor to explain. If you read the extremophile literature, what you see is that the ability to become dormant as a community is a very ancient ability that occurred in bacterial communities, probably or perhaps even at the very dawn of life on Earth. There are estimates that up to 30% of all organic life on this planet isn't even on the surface of the planet. It's buried in rock in the Earth's crust. And when you study some of these organisms, which certainly must be very, very ancient, they have a doubling time of 1,000 years. Clearly, the ability to downrate metabolism and energy expenditure is very old and central to microbial life. So under environmental stress, what do cells in a biofilm do? They reduce their size and volume almost immediately. They reduce their DNA content as much as possible. They reduce their genome sizes. They form blebs and export their DNA. They upregulate genes involved in importing and exporting DNA. Some even become ultra-microbacteria. They can become oligotrophs and live on practically nothing. They reduce mobility, and motility, and they can either increase or decrease cell adhesion. Blebbing may also rid the cell of non-essential DNA, and is a very common finding in the case we did with Rick Schwartz's case. If you notice these TEMs from Rick's case, when microorganisms undergo apoptosis, they almost always bleb, as they also do when they encounter environmental stress. As Garth Ehrlich pointed out to us in 2009, up to 30% of some organisms' genome consist of genes only involved in the import or export of DNA, and that the biofilm matrix itself is composed mostly of DNA, extracellular DNA. So commensal bacteria in eukaryotic cells have had 1 billion years to work things out between them. So it's hardly a stretch to conceive of this not only as a bacteria-to-bacteria strategy of survival, but also as a bacteria-to-host strategy to enhance commensalism or hemostasis. Indeed, We are just now starting to understand just how complex this situation is and how this extracellular DNA can moderate host defense in both positive and negative ways. The current thinking is that commensal bacteria and endodontic biofilms are composed of commensal bacteria are intimately involved in colonization resistance, which is keeping out the bad guys, and modulation of the host response so as to allow for hemostasis. If you can accept that hemostasis or disease tolerance may be the natural end toward which most hosts and microorganisms may trend, then disease is only one of the possible outcomes of an interaction between a biofilm and a host. So infection with a polymicrobial biofilm can result in one of four states: commensalism, colonization, latency, or disease. Where David and I probably disagree most is in our understanding of the latency state and what its role is in apical periodontitis. The key concept here is that when host damage is not enough to affect homeostasis, i.e. the damage is minimal, then this state is indistinguishable from commensalism or latency. It is my contention that this state is what we witness in asymptomatic apical periodontitis. And I think Dr. Epstein and Lewis gave us the key to understanding this with their explanation for why 99% of bacteria cannot be cultured. The reason is the vast majority of microorganisms on this earth grow only in polymicrobial communities. And in such communities, they are vulnerable only when they are dividing, and that they therefore use a survival strategy of dividing only when it's safe to do so. They use sophisticated signaling to know when it's safe, and when it's not safe, they go into the VBNC state where they are neither culturable or they appear to be dead. And they can stay in this state for many years and perhaps for many decades. So latent infections and the inability to culture may be expressions of the same survival strategy. It turns out that determining whether a community or an organism is either dead or in the latent state is an extremely difficult thing to do. It is even harder to determine if communities in the viable but not culturable state are even pathogenic. There is some suggestion that it remains to be determined whether cells in the non-culturable state retain pathogenicity. This would go a long way to explaining why asymptomatic areas remain quiescent for years or even a patient's lifetime. So to finish up, a few observations. Number one, the scientific community is just starting to understand the complexity of outcomes possible when multiple infectious agents occupy a single animal or invade a single host. And also, the vast majority of microorganisms live only in highly complex communities within which they have intensive interactions. And these organisms in these communities can downregulate their activity and exist in perpetuity as viable but not culturable entities. In this state, they are immune to environmental stressors. And finally, despite these observations, little is known about the factors and processes that influence these communities' assembly or stability. We make a mistake in our inferences if we consider parasitic species in isolation rather than as a community. So to end with a pop quiz, if the claimed objective of our specialty is to prevent or eliminate apical periodontitis, then this case demonstrates why our current disease model is unhelpful in our decision-making process. It provided me with no real guidance or clinical decision-making, although the prior endodontist, believing in our disease model, had absolute certainty that this patient required treatment, and the sooner the better. I like to use sickle cell anemia as an example of a really simple disease and how complex it really can be, even with a simple disease. Sickle cell anemia is the result of a single point mutation on the hemoglobin gene, the substitution of simply one amino acid with another amino acid. And You have to be homozygous for this disease to occur. So the offspring needs to have both parent genes to have the disease. Now, some of these people are very, very profoundly sick, and others aren't sick at all. And some are sick at some times and not at other times. So there's a wide phenotypic expression of this disease. If you outline a disease complexity graph of this disease, you can see it's not so simple. You have the primary molecular mutation, but then there are all the upstream and downstream modifying genes, as well as the intermediate phenotypes, which are functions of the genes unrelated to the primary effect. You also have all the environmental factors which offset disease expression, and they all contribute to a wide distribution of observed pathophenotypes. Now, apical periodontitis must be thousands of times more complex than this simple disease. So when you're confronted, like a case that Sashi posted a couple years ago on TDO, are you sure that our reductionist Cartesian disease model really gives you the guidance and the decision capability of doing the right thing for your patient? When I look at this case, what I see is the smartest thing this patient did was not have the endodontics done. And our disease model informs that decision on every single patient that we have.